All right. So as I said in email I just sent out very recently, your exam booklets are in these literature racks in this corridor outside the room. I do encourage you to pick up your exam. The email will tell you what you chose and what was the right choice, and basically learn from your mistakes or whatever. Okay? So back to business. We're looking at sunlight, and the idea here is it's just a natural continuation of the world of radio waves, the world of microwaves, off into the world of visible light. These are the same phenomena, but just different in specifics. It's electromagnetic waves are radio waves, they are microwaves. There's a patch that we don't pay much attention to, millimeter waves, and they go off then into light, both the visible spectrum and the non-visible spectrum. It's still called light. On the red end of the visible spectrum is what's called infrared. We can't see it. It's certainly part of life because you can feel it as coming from hot things. You feel the infrared light with your skin. Then go through the visible spectrum. Out the other end, you get to the ultraviolet, which again you can't see, but you are aware of from such things as sunburns. The visible spectrum has this characteristic that it's a certain portion of wavelengths and a certain portion of frequency correspondingly. It happens to be very short wavelengths, ones that are showing you is difficult because it's in the vicinity of it's a little below 1 micron, 1 micrometer wavelength, tiny little things, and the frequencies are fantastic frequencies, not millions of cycles a second or billions, but trillions of cycles per second and almost above that into the 10 to the 50 quadrillion cycles. I don't know what's next beyond that. Quintillion. Anyway, one of those big numbers. All right. As you work your way across the spectrum, you actually work your way through the rainbow colors. I'll just flip back to that because it's just to remind you this. These waves that are pure, a pure wave in this range of the spectrum, which is like in the vicinity of 700 nanometers, billionths of a meter, appears to our eyes as red. As you go to shorter wavelength, you go through orange, yellow, green, blue, the colors of the rainbow, and which you learn, I think, at school is Roy G. Biv, right? Red, orange, yellow, green, blue, indigo, violet, right? So that's just to name the pieces. If you have a certain mixtures of those pure waves, our eyes, because of how our eyes operate, see other colors that are not rainbow colors. White, for example, is not a rainbow color. It's not a pure wave. No pure wave will make you see white. However, a mixture of red, a broad swath of that spectrum will make you see white. So your eyes are interpreting what they're seeing in ways that bring to life other colors. The pastel colors, for example, are not rainbow colors. They're mixtures of other things. Any questions about sunlight itself and color and things that you're puzzled about? Okay. Going back then to Rayleigh scattering. So when light travels through empty space, nothing much happens to it. In truly empty space, it travels at the speed of light, which the name the speed of light is a little unfortunate because it's a special speed in the universe unrelated to light. It is the special speed. It has to do with relativity, Einstein and all. And it turns out that phenomena like light that have no mass, light in fact, is a massless effect. None of the, to say that shaking it won't, you won't feel anything that's peculiar because it moves too fast. In any case, everything that's massless travels at the speed of light. It has to. So that's the famous speed of light. When light encounters the atmosphere, though, it slows down a little bit. It doesn't move at its eponymous speed. It moves a little slower. And the reason for that has to do with the fact that it's now interacting with the charges in ordinary matter. It would also interact with the poles, the magnetic poles in matter, but they're so rare. The material just isn't very magnetic, with rare exception. Everything's electric. So when light encounters air, for example, it jiggles the charges. So its electric field interacts with the charges in air, in the air molecules, and it plays games with the two play together. And that playing process slows down the light. It's as though it lingers to play. The more it plays with the charge, the slower it goes. And we'll see that air slows it down by a teeny tiny amount, probably like a part in 10,000, give or take. When it goes into materials that are more dense than air is pretty fluffy stuff after all. When it goes into transparent solids or liquids, water, diamond, things that don't absorb the light but rather still play with it, it slows down a lot. In water, it slows down by a factor of 1.33. In diamond, it slows down by a factor of 2.4, because it's only going 40% of the speed of light when it's traveling through diamond. There are things actually that travels more slowly in the diamond, like a particular titanium compound known as titanium dioxide. It goes very slowly in that, and I think it's down by, gosh, I should know the number. I don't remember it all. There are two different titanium dioxides. In any case, it goes really slow, and ultimately that's the reason for titanium dioxide being a major pigment in paints and all sorts of things that are white. Nearly all the white you encounter, white paper, white clothing, they're often whitened with titanium dioxide, and we'll get there why that's the case. All right, so when light encounters air, it slows down a little bit. The other thing it does is that jiggling process of the electromagnetic wave pushing charge back and forth in the air allows for some amount of absorption of the wave and re-emission of the wave. The jiggling charges act as both a receiving antenna and then subsequently as a transmitting antenna for the waves. The wave goes in and comes out in a new direction, to a large extent random. And that happens in our atmosphere. It happens preferentially for the blue portions, the short wavelength portions of sunlight, because the particles that are present in ordinary air, the air atoms and molecules of pure air itself, are so dinky, they make terrible antennas for visible light. So terrible that you basically can neglect them. But little aggregations of air molecules, tiny dust particles, tiny water droplets, all the gunk that's present in the air, it's just teeny tiny gunk, they're decent antennas. But mostly decent antennas for the shortest wavelength parts of visible light, namely the blues, the violets, the indigos. Those waves, after all, have a short wavelength compared to, say, red. And so it's preferentially the blue end of the rainbow spectrum in sunlight that gets picked off and redirected. And that's ultimately why the sky is blue. It's called Rayleigh scattering. It's the scattering of light by particles that are too small to be good antennas for the light, but they just manage to pull it off. After all, light travels through miles and miles of air, and that's, given enough distance, even very rare events can accumulate. So when you look up at the sky, particularly on a dry day, when there's not a lot of moisture, not a lot of gunk in the air, so no big volcanic eruptions or forest fires lately, whatever. You look up and you see a very deep blue sky. It's almost dark, but there's a bit of color to it and a bit of a light to it, and that's real blue. Okay? And the blue you're seeing is not a single wavelength. It's a smear of colors across the blue spectrum, blues, indigos, violets. It's a mixture of them. The violet scatters the most strongly, after all, but it is not as bright as the blue portion of the sunlight spectrum. So the violet's more effectively scattered, but it's weaker, and so the mixture comes out into that particular color of blue. ultraviolet light, which we cannot see, is actually scattered even more strongly. And so the sky is also coming at you with ultraviolet, which you don't notice so much unless you're wearing neon clothes, the clothes that light up in so-called black light, which is ultraviolet light. You may have noticed that certain times of the day in the shadows, when you're illuminated primarily by the glow of the sky, those things glow brighter, sort of relatively brightly, those neon-y things. And that's because the ultraviolet scattering is pretty strong. You can't see it, but it's there. It's pretty strong because that's the shorter wavelength. That's shorter even than violet. Okay? Just to show you again, so this is, again, a block of silicon rubber. Yeah. And if I shine, pick a surface, there we go. If I shine white light through it, this got a lot of blue in it, actually. The blue is what preferentially gets scattered. So you're seeing, this is Rayleigh scattering. This is the scattering, it would take miles of air to do what this block does in inches, because it's so rich in tiny particles. They are truly tiny. They're 10 nanometers on a side. They're put in silicon rubber to give it strength. I know way more about silicon rubber than I ever thought I would know, because it's something I study. Anyway, and I've got tons of this stuff in my lab. So there's the blue scattered out by Rayleigh scattering. And what's left when you run out of blue is the other colors, the reds. So this is the setting sun. So at sunrise and sunset, you look at the sun and it's kind of red, right? Or, orange, red, depends on the situation. And what you're seeing is the light that's left after Rayleigh scattering sent the light out elsewhere. When the sun is directly overhead, which it never is for Charlottesville, but you go south enough, and of course there are moments where it's directly overhead. The sun has very little, its path length through the air is at a minimum. It punches right down into the air, right down to your eyes, and you see almost all the sunlight makes it to you. So you're seeing the full color possibilities of sunlight. All the blues are still there in the sunlight, which is why it's particularly harsh sun in terms of it feels like it's really beating down on you. Yes, it is. If you allow the sun to get lower in the sky, which it always is for Charlottesville, the farther north you go, the lower it gets still, even at midday. Now the sunlight has to go. It's coming in at an angle through the air. It has to travel farther through the air. It enters the atmosphere, and it's working its way at a shallow angle through the atmosphere. There's more opportunity for the light to be Rayleigh scattered. And so the lower the sun gets in the sky, the less of it, and particularly the blue parts, make it through the air and get to your eyes. When you look at the disk of the sun, when it's straight overhead, man, it's rich in blues. It's an intense blue-white light. But as it goes lower in the sky, now it's more, not as rich in blues. The blues get Rayleigh scattered out preferentially. When it's really coming in at a shallow angle at sunrise or sunset, there's almost no blue left. And all you see in the disk of the sun is red and orange. That's particularly true when the air is gunked up with tiny, tiny particles like post-volcanic eruption or forest fire, something like that. Some of these famous volcanic eruptions that have affected the whole globe for days, weeks, months, give rise to really intense sunsets. Okay? It is also possible that when the sun is low enough that the light is struggling to work its way through miles of atmosphere at this very shallow angle just simply runs out of blues. All that's left is reds, and reds don't Rayleigh scatter very well, but they Rayleigh scatter better than nothing. And so when you look up at the whole sky becomes kind of reddish. And that's because, yeah, Rayleigh scattering affects blue light more than red, but when there's no blue light left, all the blue light, for example, at sunset, all the blue light that was going to come to Charlottesville scattered away over in the Shenandoah Valley and just didn't make it to Charlottesville. All that's come through is the red light. blue light's gone. We look at our sky, and there's no blue light to scatter, to Rayleigh scatter. The sky can't be blue anymore. All that's left is red. And so you look up, it's kind of a reddish sky. All right? So any other questions about the appearance of the sun, the glow of the sky? Red, blue, so on. Okay, so at this point, you guys should all be able to explain why, when people ask you, why is the sky blue? Rayleigh scattering. All right? If the particles get bigger and bigger, which they can, and they did in that experiment that I did last time where I was growing tiny particles with a chemical reaction. Once the particles get into the size scale of the wavelength of light, then this arrangement where the blue light scatters more than the red light begins to fail. The blue light and the red light both scatter about equally. And so if the air is filled with particles that are on the order of the wavelength of light in size, or half the wavelength of light, give or take, everything scatters. Light comes in, and the word scattering is physics jargon. I sort of can't help myself to use it. Scattering just means you pick it up and you send it in a new direction. It's pretty intuitive. When the particles are big enough, all the light scatters, and you see the glow stops being blue in color and becomes white in color. And that's familiar to you as fog or clouds. You know, why are the clouds white? It's because they contain particles that are big enough to act as antennas for everything, and they're all good antennas. Actually, there's more than one way to think about this process, but this is a perfectly good one. And so the light comes in, it jiggles the charges in this big particle now, and is redirected, absorbed and re-emitted. That it's given a new name, which you don't need to remember. It's called Mie scattering instead of Rayleigh scattering, because it loses its wavelength sensitivity. And it's familiar to you as fogs. And all the white stuff you've ever seen, you're like the white of smoke, and so on. Particles that don't absorb the light and therefore give it color, produce color by the fact that they only handle, that they deal differently with the different wavelengths of light. If they just take it and re-emit it, they all appear white. All right? Bob does it. Yeah, this is the same story. All right. Next thing to think about: how do rainbows break up sunlight into the colors? So you see white light from the sun. It's the sun itself, apart from this Rayleigh scattering stuff. You see white light, but there are certainly occasions, there are many different situations in which that sunlight breaks up into different colors. You notice it during rainbows, you notice it on soap films, which we'll come to. You notice it in cut glass, gemstones that are cut, variety of other cases, where this mixture of light that we perceive as white gets separated. And we stop seeing it as a fully blended mixture and instead start seeing pieces of the mix which have color to them. So why does a rainbow do that? Or how does a rainbow work? And the story for this has a couple pieces to it. The first one is one I've already talked a little bit about, the idea that when light travels through material, it slows down. And that, in fact, the denser the material is and the more responsive its electric charge is to the electric field in the electromagnetic wave, the more the wave slows down. So different materials affect the light differently. Water, I told you, it slows down by a factor of 1.33, diamond 2.4. I mean, I only have a certain number of those sort of off the top of my head. Most of the plastics, about 1.5. Oils in the same 1.5. That slowdown factor, which is always greater than 1. One is no slowdown. That slowdown factor has got a name. It's called the index of refraction. So that's the speed. What is it? The speed of light divided by the speed in the material is the index of refraction, I guess. Anyway, it's a number bigger than 1 that tells you how much the light slows down, the factor by which it slowed down. And that slowing down process has a couple of effects. What do I say with that? One effect that's real, they're thinking of that is, this seems really off the topic, high-speed trading on the stock exchanges. If any of you guys read the book, is it called Flash Boys? Who wrote Flash Boys? Anyway, the idea that most of the trading on the New York Stock Exchange and various stock exchanges is now done by computer programs at incredible speeds, inhumanly fast speeds. And they're driven by data coming in from the various exchanges. It's all game playing. And trying to be first in playing the game gives you an advantage. And what do you need for first? You need to be like nanoseconds ahead of your competitors, literally. These tiny fractions of a second matter. And to do that, people want to put their computers as close as possible to the exchanges. Like, they will actually fight within a building that houses the exchange's computers and everybody else's computers. They will fight to be feet closer to the exchange's computers. I kid you not. And part of the exchange process takes place by way of optical cables, optical fibers, and light slows down in those fibers because it is traveling through glass. And that matters. And so there are situations in which fibers, like people were laying fibers to go from the New York exchanges to the, is it Chicago commodities exchanges. Being able to beat the competition with information back and forth there by nanoseconds or tens of nanoseconds or hundreds mattered. And going by optical fiber was the first step. But you can beat optical fiber because the light slows down in the fiber. How do you beat it? Go in open air. You can't necessarily do that with light, but you can do it with radio waves. So they go with microwave towers, trying to beat the competition and play the game a little faster than others. Okay, so enough of a crazy story, but it's real. It's going on. It's playing with your finances directly or indirectly. And the speed of light and the index of refraction of the communication techniques matters. If you can cut that index of refraction and use a technique that reduces that index of refraction, you can win out over the competition and make money. Or at least I don't know about making the money. You can take the money. All right. So that's one thing. Is the speed of light actually does matter. Certainly it affects your interactions with Europe here when you're on your gadgets and you're interacting with computers in Europe. The speed of the transaction, which again takes place through optical fibers, is affected by the index of refraction. That slows it down a little bit. But, you don't notice, but that's fine. All right. Okay, so here's another observation. Glass is more polarizable than air. So the index of refraction of glass is about 1.5. Another number I should know off the top of my head, but don't. They're all also glass is a broad category of materials, and so different glasses have different indices of refraction by some small amount. So glass is more polarizable by air by a significant amount. When a light wave moves from air into glass, the sudden increase in the polarization response of the glass causes some things to happen. And I'm giving you the choices. Part of the wave is reflected, part is absorbed, all the wave is transmitted, and some of the wave travels along the surface. How many think that some of the wave is reflected? How many think any of the other answers? No. Sorry. Yeah, the reflection is the point. I mean, this is one of these, I put these questions in years ago, and I looked at it and I was going, not so great. You're all aware that when you look in a pane of glass, you see yourself. That's not always true. If the outside is bright enough and dominates, you can't see the reflection. It's still there, but it's so dim you can't notice. So when you look at a pane of glass, you see a reflection. And this seems strange because I talked about metal surfaces providing a reflection because the wave encounters the metal, drives charge back and forth in the metal surface, which effectively absorbs and re-emits the wave in a mirror direction. The official name for the mirror direction is specular direction. But you know this idea that if the wave of light hits a metal mirror like this, like that, the reflection goes out at a specific angle. You know, if you do a laser beam, hits like that, the wave goes out like that at that angle. If it hits more steep, it goes out like that. These are the mirror angles, specular angles. Anyway, so it happens with a metal mirror. Oddly enough, it happens with the surface of glass. In fact, it happens from the entry surface of glass and the back surface of glass. You get about a 4% reflection. So 96% of the wave, if you hit the glass dead on, this is not true if you hit it at angles, but you hit the glass dead on, about 96% of the wave makes it into the glass. The other 4% comes right back at you like an echo. Very like an echo. It is an echo. It's an optical echo. And this is a general, effect that when waves encounter surfaces and change speed in going from one side of that surface to the other, basically when it crosses the interface, if the wave changes speed, part of it reflects every time. This is true not only for light, it's true for sound. When I'm talking here, it's going through the air, it encounters the wall surfaces. My voice encounters the wall surface. Sound can travel through solids. It typically travels very fast through solids, much faster than in air. It also travels through water much faster than in air. And the result is there's a reflection off that interface. For sound, the change in speed is huge, and the reflection, therefore, is huge. The worse the change in speed, the bigger the reflection. And so sound bounces like crazy off of solid surfaces, brick buildings and stuff. If you go over in these quads and stuff with all the brick buildings and clap your hand, you'll hear it coming back from every surface. And that's an effect of this failure this problem of crossing the interface and changing speeds. All right? I mean, why does changing speeds cause a reflection? At this level of the class, I'll just say because. If you actually do the mathematics of the crossing, it has to happen. You have to have that reflection. So when light changes speed by a factor of about 1.5 in going into glass, reflection. How much reflection? About 4% of the intensity, of the brightness of the light, the power carried by the light. When it changes speed at the far end, in going from inside the glass, where it travels relatively slowly, to enter the air, where it's speeding up, how much reflects? About 4% again. That reflection tries to go back out and come to you. Most of it does, but part of it reflects again. So light can actually get trapped in the glass. It enters once, hits the back, comes out, tries to escape. Part of it reflects, part of it reflects, part of it reflects, part of it reflects. It gets dim very fast, but it makes a bunch of bounces before it's finally down to essentially zero. As we'll see, as you get shallower angles, you get more reflection. And ultimately, it's sort of a special case. But if you hit the glass at a shallow enough angle, and it's a little more complicated than that, once you get the wave inside the glass, it will bounce off the surfaces indefinitely. And that's the concept of an optical fiber. The light actually follows the glass. It can't get out at all. But we'll get to that. That's down the road. All right, so the main thing is light entering the glass partly reflects, partly goes in, and when it tries to leave, it partly reflects as well, partly gets out. All right? So that's the reflection effect. There's a second effect, and I'll show you both of these things in a second. There's a second effect when the wave encounters the interface. If it encounters the interface straight on, perpendicular, it just punches right in and goes straight afterwards. But if it hits the interface at an angle and slows down or speeds up, its direction of travel bends. And a simple way of thinking about why this happens, let me illustrate it. I don't want to. How am I going to do this? I'll do it like this. I'm going to be a wave, okay? So I'm waving like this. Yeah, you can laugh at me, laugh with me, laugh at me, whatever. So I'm going to go on, and once I get into this plate of glass, I'm going to slow down. So here I am going along. Which part of me encounters the wave, encounters the glass first? Well, it's my left hand. It slows down first. And so it bogs down. It's having trouble moving. And then more of me hits, more of me hits, more of me hits. and I start heading like this in. I turned. I went from going like this to like this. Can you see the turn? My right side turned more than my left side, or at least it was out in the air longer, and it managed to make more progress. And so waves entering, passing through an interface in which they slow down, they steer toward the perpendicular to the interface. The perpendicular to the interface is this. This is perpendicular to the interface, right? So a wave that slows down steers toward that interface. On exit from a slow material, like coming out of the glass, the result is reverse. The part that comes out first is over here on the left side. It gets ahead now, and the wave bends away from the perpendicular as it speeds up. So light bends toward the perpendicular to the interface on slowing down, and away from the perpendicular on speeding up. Is that language okay? Can you follow that idea? Let me show you this. So I'm going to do it on this. We're going to stare down from this camera at light passing through a block, a transparent block, and I'll put it up in this center projector screen. You'll have to remind me to undo this, because otherwise I'll do it, and I'll lecture about the slides that aren't there anymore. There we are. Here come the light waves are coming along like this. They're encountering the plastic surface that is right here. And you can see they bend? And they're bending toward the perpendicular. That's the perpendicular to the surface. My finger is perpendicular to that. As they slow down, they bend toward the perpendicular. And as they come to the back and try to speed up, they bend away from the perpendicular. You're all okay? This fits what I just described for you. At the same time, so this phenomena is known as refraction, just to give it a name. The bending of light as it changes speed at an interface. So refraction. You may have gone and had your eyes checked. If not now, then when you turn roughly 40, you'll lose your ability to accommodate distance very well, and you become nearsighted or farsighted. And you will want to go in and have your eyes checked, and they're sort of checking your refraction, because your eyes operate using this phenomena, this changing of speed causing the bending of light. That's how your eyes, the lenses in your eyes, and your cornea in general, are using this phenomena to allow you to see and tell where things are and what you're seeing in front of you. Okay, so that's refraction. The other effect that occurs, which I told you about, is reflection. And that should also be here. It's a little trickier to see because about 4% of the light that's hitting that surface is reflecting. Can I get it to appear? Where is it? There it is. I have to block out the room light. Okay, I'll turn off the room light. Oh, well, that was great. I could see it for a minute, and then it got. How do I trick this camera? Turning the light on will not help. Oh no, for all I know, it will help. Stupid camera. It'll come back. This is auto irising stuff. Can I defeat the auto iris? Maybe I can do that. Maybe, let's see. Is it going to give me? No. Too much automation here. The reflection's right here. I have to block out the room light. Oh, it's so visible for a little while. Okay, I'm going to go to nothing and try to trick the iris into. Uh-oh. There it is. Can you see them? Can you see the reflected lights? Finally! We have to defeat the engineer's bad planning here. They're the reflections. All right. I'm happy. So both of these phenomena are important for Rainbows. If you remember, I'm trying to tell you about how rainbows work. They're based on, so far, on reflection and refraction. We need them both to have a rainbow. And we need one more thing. The remaining thing is that the speed of light in materials is sometimes, well, I guess always to some extent, dependent on wavelength. When I said that light slows down by a factor of 1.5 and going to glass, that's an approximation, and it turns out it's not quite true for all the different wavelengths. Some wavelengths slow down a little more than others. It's a subtle effect usually, but there's a little bit of wavelength dependence, or equivalently frequency dependence. And the general rule is that the blue end of the visible spectrum travels more slowly through materials than the red end. It has to do with resonances in the material. That for a piece of glass is essentially indifferent to the wavelengths of light. The charges jiggle back and forth as visible light goes through, but they don't really get excited about it. In the ultraviolet, though, there are wavelengths and therefore frequencies at which the charges actually get sloshing like tank circuit stuff, resonances, and really interact with the light. And the closer you get to those resonances, the more the light slows down. And therefore, the blue end of the spectrum, which is closer to the resonances you never see, gets slowed down a little more than the red end. It's a little closer to those resonances, to the favorite frequencies in the material. And so blue light travels more slowly than red light. And because blue light travels a little more slowly than red light, blue light also bends a little more than red light at interfaces. When this white light going into that piece of plastic, it bends and it looks still like the white beams are exactly still all together, everything's good. But not quite. The blue light bent a little farther than the red light. And it gets a little spatially separated by the end of the block from the red light. And then they go out, they come out the other end, and then they bend, they undo the bend. If we design things correctly, though, you can make this separation, you can make this difference in the speeds of the different colors of light, and therefore the changes in refraction, you can make them quite visible. Incidentally, the name for this phenomenon, where the different colors travel at slightly different speeds, is called dispersion. Pretty intuitive name for it. The wavelengths get dispersed. And so what we got here is a prism filled with a liquid that's evidently pretty good. First off, it has a fairly large change in speed, about 1.5, like glass, but it also has a lot of dispersion to it. It really, really favors, slows down the blues, not so much the reds. And they get separated. So when I turn this on, and I turn off that screen, and I get nothing. I turn this light on and get light. Let there be light. All right, yes. Okay. The red light, which travels faster because it doesn't bend as much. In going into this prism, the light hits one surface, bends, hits a second surface, bends again. Because it's cut in a way that it just keeps on, the bend accumulates rather than canceling the way it did over there in that block. And so the red light, which travels slower, faster, doesn't bend as much. It's simply not affected as much by the prism. It enters traveling almost at the famous speed of light in air. It goes into liquid. It slows down a lot, but not that much. And then it speeds back up. It just doesn't bend very much because it doesn't see those interfaces as really big deals. So it goes closer to straight. Straight would be hitting the ceiling. It doesn't go straight. It goes and it gets kicked over here to the side. The blue end of the spectrum, however, gets really bent hard. So this is, rainbow, our version of a rainbow. That is starting with essentially white light from an incandescent light source. And remember, this is a source of light that it's creating a thermal spectrum of light. That is the light that is emitted by a hot object by virtue of the thermal motion of its charged particles. Because the incandescent light bulb's surface there isn't hot enough, it's only half, say, the temperature of the sun, It's rich in reds, but it's kind of wimpy in the blue end of the spectrum. It's not hot enough to create the blues that are present in sunlight. So the blue end here is kind of dim. If I could have sunlight coming up out of this box, that would be that blue end would be just as bright as the reds and the yellows. Okay, so we have to make do. So it's a rainbow if we had a dim, tired sun that wasn't like our sun, but rather a red one. So the phenomena here is dispersion and refraction and dispersion are working together to create that. Couldn't turn it on, can't turn it off. All right. So that then brings us to the rainbow. Rainbows occur when the sun is relatively low in the sky. You might have never paid attention to when you see rainbows, but you do not see them at midday in Charlottesville, when the sun is coming straight down or nearly straight down. You want the sun coming in at a shallow angle, as it would, say, in the late afternoon, and you want to have it coming in over your back. So the sun's behind you, it goes over your back, and it illuminates droplets of water. Where do the droplets come from? Raindrops. Mist will do in some cases. They need to be particles that are big enough to be. You want big enough droplets. Raindrops, despite your having seen them drawn as tear-shaped things your whole life, they're not tear-shaped at all. They're spherical. Raindrops, when they're falling, are pulled into almost perfect spheres by the surface tension in the water. The outside surface of the water is unhappy and wants to minimize itself. It doesn't have enough neighbors around it. It pulls in like a taut trampoline surface. And the shape given a certain volume of water, the shape that minimizes the surface is a sphere. So raindrops as they come down, are little balls. You can see this if you take flash photographs of rain. You'll see they're just little balls. Anyhow, so the balls are off in the distance. The light is coming across, hitting them. So it requires this special arrangement where you've got rain on one side and open sky for the sunlight on the other. And when the light hits the raindrops, it bounces around inside the raindrops, and some of the light comes back at you. And the bounce that matters the most, and people studied this some time back, there are lots of crazy paths through the raindrops, but the dominant one, the one that's most important and the one that contributes to the main rainbow, there's more than one kind of rainbow. There are double rainbows and stuff. They have more complicated paths. But the one that matters for rainbows, here we are. The sun is coming in over our shoulder. It's hitting these droplets. It does a couple things. The light enters the raindrop on its upper part of its face. It's somewhere around where I've drawn it in this drawing. The light refracts on entry. It bends, after all, toward the perpendicular, right? It's slowing down. So it bends toward the perpendicular, and it bends, the more it slows down, the more it bends. So the violet end of the spectrum bends more than the red end of the spectrum, which is why I've drawn this. So the violet wavelet, the little piece, is bent harder than the red part. So they're getting separated in space, and certainly in angle. That light goes to the back of the raindrop, and the vast majority of it goes out the other side, gone, uninteresting, except about 4%, 3 or 4% reflect off that back surface, because when the light speeds up in trying to exit the raindrop, some of it reflects. That change in speed, again, creates the echo. So here it comes back. The red and the violet portion are reflecting off the back. They're traveling slightly different paths, and they burst out of the front of the raindrop. There's a little reflection there too, but that's uninteresting as well. The part that breaks through is interesting. And when all is said and done, light that entered as a white streak hitting that top surface of the raindrop comes out slurped across in space. The violet is aimed high relative to the red. And when you look with your eyes at these raindrops sending light toward you, when you look for red light, you see it in the higher raindrop. The raindrop that you're seeing is up high because its red light is coming down toward you. Its violet light misses you. It goes over your head. Someone else can see that. So you see a red glow from up high. And if you look a little lower in the sky, you see the violet portion of light sent by the lower raindrops. So you're looking at different raindrops, and you see that the highest raindrops are sending you their red light. The lowest raindrops are sending you their violet light. The other lights are there, you're not in their path. And this is true not just in height. It's actually an arc. If you take a line that goes from the sun through you and over towards where the raindrops are, there is a circular path around that axis. And the inner part of that circular path will send its violet light toward you. The outer part of that circular path will send its red light toward you. You can see the whole rainbow when you're in an airplane and you look at the droplets that are in clouds. You can see a rainbow that's the whole circle. On the ground, of course, you only see the top half of the circle because the bottom half would be there, except the dirt's in the way. All right? So to see a rainbow, you got three phenomena that all have to show up: refraction, reflection, and dispersion. All right? Any questions about how a rainbow works? Okay, I think I've got one more demonstration. Well, I've got two, but I'll deal with one. Yeah, diamonds sparkle. I'm not going to ask this question. Diamonds sparkle so well because they first of all, they slow light down a lot. Light goes only at 40% of full speed through diamond. Therefore, the reflections are ferocious from the surface, more like 10% from each surface. Big reflections. There's also a lot of dispersion. The blues travel much slower in a diamond than the reds, and consequently, there's the paths that the red and blue light take after entering these facets are quite different. You can get it so that only green light manages to come out of a certain facet as a reflection. The red light associated with that same portion of sunlight has been sent somewhere completely different. All right, what I wanted to talk about was the reflection from something like a soap film. And when sunlight encounters a soap film, so it's a very thin layer, and it doesn't have to be soap. It can be anything where you got a very thin layer of glass will do this. There are reflections from both the top surface and the bottom surface, after all, and something like 4% from each surface. And a single wave of sunlight is full of lots of waves. Each individual wave created by an individual charged particle on the sun's surface. But each little wave travels along, and when it encounters the surface, that individual wave actually gets broken up into some pieces heading in different directions. And some of it works its way into the soap film, bounces around a bit, but you can get a piece of the wave coming off the top surface and a piece of the wave that came off the bottom surface and worked its way back out of the film. So when you look with your eyes at the reflection from a soap film, you're seeing waves. Every wave that hit the soap film is coming at you, part of it's coming at you from two different paths, one of which came off the top surface alone, and one of which actually entered the surface and came back out. And the result is those pieces of wave have traveled different distances, and they consequently, you may be seeing different parts of the wave. You may be seeing the crest of one part of the reflection and a later crest of the other part. Or you may be seeing a trough where the electric field's pointed the wrong way. So the wave comes along. The waves that you're seeing are pieced together from several paths, and they may or may not be in phase with one another. The waves that are in phase, or wave pieces that are in phase, have electric field up at the same time, electric field down at the same time, and they work together to make you see bright light. Wave pieces that are out of phase, one of them has electric field up and the other has electric field down, and they work at cross purposes to make you see nothing. And the path length differences will bring different colors into constructive interference. Some wavelengths will experience constructive interference, whereas other wavelengths will experience destructive interference, and you won't see them at all. So I'm going to dip to create a soap film here, send light at the soap film, and it should show up, if we got this right, it should show up on the screen if I turn the lights out. Initially, it's colorless, but as the soap film loses moisture and gets thinner, it starts to develop colors. Can you see the colors? Wherever it's green, that is telling you that green light has about the right wavelength, that in going through the film and coming off the back surface rather than coming off the front surface, the wave has experienced an integer number of wavelengths. And so the two reflections are in phase and add constructively, and you see bright green. At the same time, you don't see bright pink because the reds and yellows didn't travel the right distances. They're out of phase. They're killing each other off. You see only, so you see one portion of the spectrum or another. You can actually measure how thick the film is by looking at the colors, and it's often used for that purpose. If you want to know what very thin things are, how thick they are, you look at these sort of, this is called interference patterns. These are interference colors. We're now getting to the point where most of the film is on the order of one wavelength of light. It starts becoming gray. It loses its color distinction, and then it bursts. But that's the idea. Okay? So, last bits of sunlight on Friday.